Welcome to Lecture 7, Database Applications. This is Professor T. Freed Muhammad. We will be discussing in this lecture the three components of client-server systems: presentation, processing, and storage. We'll also distinguish between two-tier and three-tier architectures, describe key components in information flow in web applications, describe how to connect to databases in three-tier applications using Java Server, technically GSP, it's a connector, and the Python. We'll understand the notion of transaction integrity. We'll compare the optimistic and pessimistic concurrency control and understand the basics of application security. Let's look into the client-server architecture with a use case. Client-server applications began with the advent of network computing and are the dominant paradigm for computing applications for the past 25 years. Prior to the mainframe computers with dumb terminals and later smart terminals was the dominant mode. These still exist, but they are usually also somehow connected to computer science network or client-server networks. Client-server architecture and database management systems can be thought of as a way to organize and manage data efficiently, much like how a university handles student information. Imagine a university system as our use case, where students need to access their grades, course schedules, and personal information. In a client-server architecture, the server is like the university central database, which stores all this information securely. The clients are the students' devices such as laptops or smartphones, which they use to access this information. When a student wants to check their grades, their devices, the client sends a request to the university database, the server. The server processes this request, retrieves the relevant information from the databases, and send it back to the student's device. This setup ensures that the data is centralized and managed efficiently. For example, if a student updates their contact information, the change is made in the central database, and everyone who accesses this information will be updated as well. This is much more efficient than having multiple copies of the data spread across different devices. Client-server architecture enhances security and data integrity. Since the data is stored in a central location, university can implement strong security measures to protect it. Only authorized clients like students and faculty can access or modify the data, reducing the risk of unauthorized access or data breaches. This architecture also allows for better maintenance and updates. If the university needs to update the database software or add new features, they only need to do it on the server side without affecting the clients. This ensures that the system remains up to date and reliable for all the users. This figure 7.1 shows the application logic components. It has graphical user interface through the browser, GUI or GUI. The presentation logic, input and output, happens there. Procedures, functions, programs. We use processing logic, which is input-output processing, business rules, data management, and the DBMS activities happen under the hood. The storage logic, data storage and retrieval happens simultaneously. As you can see here, there are three main layers in an application, and they serve different purposes. The presentation layer is what the user directly interact with. The processing logic involves the software doing all the computation for the application, and the storage logic involves the activities of the DBMS. Different types of client-server systems will distribute these three different waves. We are going to see the different types of applications partitioning. This involves distributing the presentation, processing the storage and storage logic to different computers in the client-server network. Of course, presentation is always at the client. the FAT versus thin clients. The fat client is a client PC that is responsible for processing presentation logic, extensive applications and business rules logic, and many DBMS functions. Thin client, an application where the client or the personal computer or device accessing the application primarily provides the user interfaces and some application processing, usually with no or limited local data storage. Let's look into this with an example. Let us take an example of a flower selling business. Understanding the concepts of fat and thin clients in a client-server architecture can significantly impact how the business operates and manages its data. Let's explore these concepts in a little bit more detail. In a fat client setup, each client device, such as cash register, tablet, or computer used by the flower shop, as we are taking flower shop as our example, has significant processing power and can perform many tasks independently of the server. For instance, a fat client might have its own software to manage inventory, process sales, and generate reports. This means that even if the connection to the central server is lost, the device can still function to some extent. For example, a cashier could continue processing sales and the data would be synchronized with the central server once the connection is restored. Fat clients are beneficial because they can reduce the load on the server and provide a more responsive user experience. However, they require more powerful and expensive hardware, and maintaining software updates across multiple devices can be challenging, whereas thin clients, on the other hand, rely heavily on the server to perform most of the processing tasks. In a flower shop, which is our running example here, a thin client might be a simple terminal or web browser that connects to the central server to access the point of sale system, inventory management, and customer data. The server handles all the heavy lifting, such as processing transactions and generating reports. This setup is cost effective because it requires less powerful hardware on the client side. It also simplifies maintenance as the updates only need to be applied to the server. However, thin clients are highly dependent on stable network connection. If the connection to the server is lost, the client might not be able to perform any tasks until the connection is restored. Choosing between the fat and thin clients. The choice between the fat and thin clients depends on the specific needs and the resources of the flower selling business. Fat clients might be more suitable for larger businesses with multiple locations that need to operate independently. They can also be beneficial if the business requires complex, resource-intensive applications that are best run locally. Thin clients, however, are ideal for smaller businesses or those looking to reduce costs. They are also good choice if the business has a reliable internet connection and prefers centralized control over the data and applications. Many businesses opt for a hybrid approach combining elements of both fat and thin clients. For example, the flower shop that we are looking into might use thin clients for the basic tasks like processing sales and accessing inventory data, while fat clients are used for more complex tasks like generating detailed reports or managing supplier relationships. This approach can provide a balance between cost, performance, and reliability. It also allows the business to adapt to changing needs, such as expanding to new locations or adding new services. Understanding the difference between fat and thin clients can help the flower selling business make informed decisions about its technology infrastructure, ultimately leading to more efficient operations and better customer care. The common logic distributions, two-tier client-server environments. Let's look into this with an example, and let's continue learning using the flower shop as our running case. Local area networks are typically implemented as a two-tier system. Here, the presentation layer always does presentation logic, and the server always does storage logic. Processing logic could take place in either. This is what you are using when you work within the office local network or your school local labs. This is how it is done on the web. There are at least 3 tiers, with each tier doing one of the 3 logics. The client is you on your PC or mobile device. Application logic takes place on the application server and the DBMS on the database server. We'll see the later slides. Some code you'll typically use in application logic. Notice that sometimes the processing logic is split. The underlying business logic is done on one server and the control of internet processing is done on the web server. Web application components. Let's look into this with a running example. So let's look into a library system. A web application allows users to interact with the library's resources and services through web browser. The system is typically composed of several key components that work together to provide a seamless user experience. At the heart of the web application is the user interface, which is what patrons see and interact with when they visit the library's website. This interface is designed to be user-friendly, permitting patrons to search for books, reserve materials, and access their accounts easily. It includes elements like search bars, navigation menus, and interactive forms that make it simple for users to find what they need. Behind the scenes, the web application relies on server to process requests and manage data. When a patron searches for a book, the request is sent to the server, which then queries the library's database to find matching results. The server acts as intermediary, handling all the computations and data retrieval tasks so that the user interface can display the information quickly and efficiently. The server also manages user authentication, ensuring that the only authorized patrons can access the certain features, like viewing their borrowing history and reserving the books. This component is critical and crucial for maintaining the security and integrity of the library's data. Another essential component in the database, which stores all the information the library needs to function. This includes details about the books and other materials in the collection, patron information, and transaction records. The database is structured to allow for efficient searching and retrieval of data. For example, when a patron searches for a book by title or author, the database can quickly return relevant results. The databases also support complex queries, such as finding all the books in a specific genre that are currently available for checkout. This component is vital for ensuring that the library's resources are easily accessible and well designed. Additionally, the web application may include various services and APIs that extend its functionality. For instance, the library system might integrate with external databases to provide access to ebooks, academic journals, or other digital resources. These services can enhance the user experience by offering a wider range of materials and tools. The application might also include features like automated notifications, which remind patrons when their books are due, or recommendation engines that suggest books based on the patron's reading history. These components work together to create a comprehensive and user-friendly library system that meets the needs of its patrons. The network protocol for internet-bound traffic as TCP/IP, or Transmission Control Protocol, Internet Protocol, which stands, as I just mentioned. The notion of an extranet is what we usually think of when we use a website like Amazon. Companies interact with the public via extranets and intranet. And intranet also uses 3-tier internal technology, web servers, TCP/IP and protocol, which is limited to access from within the organization control. This is hidden from the external internet by the firewall, providing security for the organization's resources. This shows the difference between the static and dynamic page requests. Any web request to a .html or .shtml file is a static request No application processing take place on the application server. Basically, the file retrieved has all the HTML, CSS style sheets and JavaScript code on it. URL or universal resource locator with .jsp, .php, and .aspx are dynamic page requests. Here, the application server is invoked and it interacts with the database to dynamically generate the HTML, CSS, and JavaScript that gets sent to the browser. In a three-tier architecture, the flow of information is organized into three distinct layers, as mentioned earlier, each of its own responsibility. So the setup is particularly useful in the context, let's say we establish a context of a cybersecurity services provision organization, where managing and protecting data is crucial. Let's break down how information flows through these layers using cybersecurity services company as an example. At the first layer, known as the presentation layer, users interact with the cybersecurity system through a user-friendly interface. This could be a web application or a software dashboard that cybersecurity analysts use to monitor network activity, detect threats, and respond to security incidents. When an analyst logs into the system, they enter their credentials through this interface. The presentation layer then sends this login request to the next layer, the application layer, for processing. This layer is all about making the system accessible and easy to use, ensuring that analysts can quickly navigate and understand the data presented to them. The application layer, also known as logic layer, is where the core functionality of the cybersecurity systems resides. When the application layer receives a login request from the presentation layer, it processes this request by checking the credentials against the stored user data. This layer contains the business logic and determines how the system should respond to various input and requests. For example, if an analyst requests a report on recent security incidents, the application layer will generate this report by querying the necessary data from the database and performing any required calculations or analysis. Once the report is ready, the application layer sends it back to the presentation layer to be displayed to the analyst. The third layer that is also known as data layer is where all the information is stored and managed. In a cybersecurity context, this includes data on network traffic, detected threats, user accounts, and security policies. When the application layer needs data to process a request, it sends a query to the data layer. Let me retrace back. The data layer, then when an application layer needs data to process a request, it sends a query to the data layer. The data layer then retrieves the relevant information from the database and sends it back to the application layer. This layer is crucial for ensuring that data is stored securely and can be accessed quickly when needed. It also handles data backup and recovery, ensuring that important information is not lost in the event of system failure or the security breach. The flow of information in a three-tier architecture is designed to be efficient and secure. By separating the presentation, application, and data layers, the system can handle multiple requests simultaneously without compromising performance. Each layer communicates with the others through well-defined interfaces, ensuring the data is processed and transmitted securely. For example, when an analyst detects a potential security threat, they can input this information through the presentation layer. The application layer then processes this input, updates the threats databases in the data layer, and triggers any necessary alerts or automated responses. This architecture enhances the system's flexibility and scalability. If the cybersecurity company needs to update the user interface, then they can do so without affecting the underlying application logic or data storage. Similarly, if they need to expand their data storage capacity, they can do so without disrupting the other layers. This modular approach allows the system to evolve and adapt to new challenges and requirements, ensuring that the cybersecurity services company remains effective and reliable. No matter what client-server architecture you use, you will encounter middleware and APIs. There are many kinds of APIs and databases. With APIs are only one type. For example, there are APIs for the presentation layer stuff, forms, buttons, list boxes, and all other user interfaces processings. There are also APIs for working with different web services. Often these are in the form of REST or representational services and XML. Computer programmers and application developers will use APIs for interacting with the database, and these APIs invoke middleware to provide the connection to the DBMS. OODBC or ODBC and ADO.NET are the most common database APIs and for the Microsoft platform. ODBC is older and ADO.NET is more modern. ADO.NET is most common database API in web applications. Using databases via middleware APIs, let's say we have taken a flower sales business before, involving several steps that ensure efficient data management and retrieval happens. So number one, identify and register database driver. Before the flower shop can interact with its database, it needs to identify the register the appropriate database driver. This driver acts as translator, permitting the shop's software applications to communicate with the database system. For instance, if the flower shop uses MySQL database to store customer orders and inventory, it would need to register a MySQL driver. This step ensures that the middleware can correctly interpret and execute database commands, enabling seamless data operations. Number two, open a connection to a database. Once the driver is registered, the next step is to establish a connection to the database. This is akin to opening a communication channel between a flower shop's software and database. For example, when a customer places an order through the shop's website, the system opens a connection to the database to access and update the inventory levels. This connection allows the system to retrieve information about available flowers, process the orders, and update the stock accordingly. Number three, execute a query against a database. With the connection established, the system can execute queries to retrieve or manipulate data. In the flower shop, a query might be used to check the availability for a specific type of flower or to retrieve customer details for loyalty programs. For instance, when a customer searches for the red roses, the system executes a query to find all entries in the inventory that match this description. This step is crucial for accessing the necessary data to fulfill customer requests and manage operations efficiently. Number four, process the results of the query. After executing the query, the system processes the results to provide a meaningful information to the user or application. In the flower shop context, this could involve displaying the search results for red roses on the website or generating reports on daily sales. For example, if a customer searches for a bouquet under $50, the system processes the query results to filter and display only relevant products. This step ensures that the data retrieved from the database is presented in a useful and understandable format. Number five, repeat steps 3 and 4 as necessary. The process of querying the database and processing the result is often iterative. In the flower shop, this might involve multiple queries to gather all the necessary information for an order. For example, the system might first query the inventory to check flower availability, then query customer data to apply any discounts, and finally update the order status. Repeating these steps ensure that all required data is accurately retrieved and processed, supporting smooth business operations. Number six, close the connection to the database. Once the necessary queries have been executed and the results processed, it is important to close the connection to the database. This step is essential for maintaining the efficiency and security of the database system. In the flower shop, closing the connection ensures that resources are freed up for other operations and prevents unauthorized access. For example, after processing customer's order, the system closes the database connection to secure the data and prepare for the next transaction. This practice helps maintain the integrity and performance of the database over time. Here's the Java code for doing the steps from the previous slide. The driver is the middleware program that provides a link to the DBMS. At the open a connection step, you can see the connection string, and further down you see the query. The data returned from the query is in a result set, and your program can loop through this result through set to obtain the data. The JDBC or Java Database Connectivity classes that you will likely use in Java database programs are driver, driver manager, connection statement, and result set. Each of these are classes of Java Database Connectivity API application interface. So this textbook shows a Python application that involves a database server, various Python classes executing on an application server, and output of a web client. JavaScript object notation or JSON is the data interchange format that is both easy for humans to read and for machines to parse and generate. We looked at the stored procedure in chapter 7. A stored procedure is actually a database object like the table or a view. With the stored procedure, application logic is taking place on the database server. Transactions are discussed in chapter 12, and the idea here is that a transaction should be atomic, and that means either the whole thing is done or none of it is done. So updates within the transaction are not finalized until the transaction commits. If the error occurs anytime along the way, then that is the data is rolled back, canceling previous updates and in the transaction. As you can see, developers of web applications need to be careful about how they establish database connection. Advantages and disadvantages of stored procedures. Let's look into this with an example. Stored procedures offer several advantages in managing a flower sales business, as a running example, particularly in terms of efficiency and security. One of the primary benefits is improved performance. Stored procedures are pre-compiled and stored in a database, which means they execute faster than ad hoc queries sent from an application. For instance, when processing a large number of orders during peak seasons like Valentine's Day, stored procedure can quickly retrieve and update inventory levels, ensuring the customers receive accurate information about flower availability. Additionally, stored procedure enhance security by permitting the database administrator to grant users permission to execute the procedure without giving them direct access to the underlying tables. This is particularly useful in a flower shop setting where employees might need to access order data without having or being able to modify sensitive customer information. However, stored procedures also come with certain disadvantages. One significant drawback is the complexity of maintenance. Since the stored procedures are stored in a database, any changes to the business logic requires updates to the procedures themselves, which can be more challenging than modifying application code. For example, if the flower shop decides to change its pricing strategy, the stored procedure that calculates discounts would need to be updated accordingly. This can lead to increased maintenance efforts and potential downtime. Another limitation is the lack of portability. Stored procedures are often database specific, meaning that they might not work if the flower shop decides to switch to a different database management system. This can limit flexibility and make migration more complicated. Despite these drawbacks, the efficiency and security benefits often make stored procedure a valuable tool in managing database operations for a flower sales business. The three-tier architecture makes it easy to distribute the computational burden across different computers. This increases scalability and impact all the factors in the list. Transaction integrity is enforced via ACID or ACID compliance. ACID is kind of a mantra when it comes to relational database management system. This is not true for all the data sources. However, for example, most XML data that is exchanged over the internet is not ACID compliant. For securing data integrity and transaction processing system through ACID is essential. Let's look into this with an example. ACID or ACID is an acronym, stands for Atomicity, Consistency, Isolation, and Durability, representing a set of properties that ensure reliable processing of database transactions. In the context of flower sales business, understanding ACID is crucial for maintaining the integrity and reliability of transactions such as processing customer orders and managing inventory. Atomicity ensures that each transaction in a database is treated as a single unit which either completes successfully or fails entirely. In the flower shop, this means that when a customer places an order, all parts of that transaction such as updating the inventory, recording the sale, and processing the payment must be completed successfully. If any part of the transaction fails, the entire transaction is rolled back and the system returns to the previous state. For example, if the payment processing fails, the inventory levels and sales records are not updated, ensuring that there are no partial or incomplete transactions that could lead to inconsistencies. Consistency guarantees that the transaction brings the database from one valid state to another, maintaining the database's predefined rules and constraints. In the flower shop, consistency ensures that the database accurately reflects the current state of inventory and sales. For instance, if a customer orders a bouquet of roses, the system checks that there are enough roses in stock before processing the order. If the stock is insufficient, the transaction is not completed, preventing the system from recording a sale that cannot be fulfilled. This ensures that the database remains accurate and reliable, reflecting the true state of the business at all times. Isolation ensures that transactions are executed in isolation from one another, preventing them from interfering with each other. In the flower shop, this means that multiple transactions, such as several customers placing orders simultaneously, do not affect each other's outcomes. For example, if two customers are ordering the same type of flower at the same time, isolation ensures that each transaction is processed independently, preventing issues like double selling or the same inventory. This property is crucial for maintaining data integrity, especially in high traffic situations like holiday sales. Durability guarantees that once a transaction has been committed, it will remain so even in the event of system failure. In the flower shop, durability ensures that all completed transactions such as recorded sales and inventory updates are permanently saved in the database. For instance, if the system crashes after processing a customer's order, durability ensures that the transaction is not lost. When the system recovers, the transaction remains intact and the sale is still recorded. This property is essential for building trust with customers, as it ensures that their orders are reliably processed and recorded, even in the face of technical issues. Together, these ACID properties provide a robust framework for managing database transactions in a flower sales business, ensuring that operations are reliable, accurate, and secure. SQL transaction sequence or pseudocode environment. You look at begin transaction and end transaction, and you can insert order ID, order date, customer ID into order T. Insert order ID, product ID, and then this can go on. This is valid information inserted. Commit to work. All changes to the data are made permanent. Invalid product ID entered. Transaction will be aborted. Roll back all the changes made to the order T. All changes made to the order T and order line T are removed. Database the state is just as it was before the transaction began. we are going to see that multi-user environments add some complexity. The lost update problem is one reason, but as we'll see, solving the lost update problem could lead to another problem called deadlock. We'll explore this in next few slides. So the idea here is that if two programs can read and write to the same record at the same time, then one may step on another, thereby negating the effects of one program. How do we prevent this? Through locking. Let's talk about that next. The idea here is to accomplish serializability. This is usually done via locking. Locking mechanism, the most common way to achieving serialization. Data that is retrieved from the purpose of updating is locked for their updater. No other user can perform updates until the data is locked. As you can see from this figure, locking helps to alleviate the lost update problem. You can lock at the table level or at the record level, and you can lock for updates only for updates plus queries. There are SQL commands for locking, and most DBMS adopt default locking, record level and update mechanisms. Here we see the details and type of locks and level of locks. Let's look into this with an example. In the library system, let's take that as an example. A locking mechanism is essential for managing concurrent access to the database, ensuring that multiple users or processes can interact with the system without compromising data integrity. Locking mechanisms control how data is accessed and modified, preventing conflicts and inconsistencies that can arise when multiple transactions occur simultaneously. One common type of locking mechanism is the pessimistic locking, which involves locking a resource as soon as the transaction begins, preventing other transactions from accessing or modifying the data until the lock is released. In a library system, this could mean that when a librarian is updating the status of a book, marking it as checked out, the system places a lock on that book's record. This lock ensures that no other librarian or automated process can modify the book's status until the update is complete. While pessimistic locking ensures that data consistency, it can lead to reduced concurrency as other transactions must wait for the lock to be released before they can proceed. This might cause delays, especially in high traffic situations such as during peak borrowing times. An alternative approach is optimistic lockings, which allows multiple transactions to access and modify data concurrently. Assuming that the conflicts are rare, in this scenario, the library system does not lock the data initially. Instead, it checks for conflicts before committing a transaction. For example, if two librarians attempt to update the same book record simultaneously, the system will check whether the data has changed since it was last read. If the conflict is detected, one of the transactions is rolled back and the user is notified to retry. Optimistic locking improves concurrency and performance by reducing the time data is locked, but it requires additional logic to handle conflicts and may not be suitable for environments with frequent data contention. Deadlocks are the potential issues in locking mechanisms occurring when two or more transactions are waiting indefinitely for each other to release locks. In a library system, this could happen if one librarian holds a lock on a book record while waiting for another record locked by a different librarian and vice versa. To prevent deadlocks, the library system can implement strategies such as timeouts, which automatically release locks after a certain period, or deadlock detection algorithms that identify and resolve a circular wait condition. Effective management of deadlocks is crucial for maintaining system performance and ensuring that transactions can proceed without unnecessary delays. Locking mechanisms play a vital role in maintaining data integrity and consistency in a library system by managing concurrent access to the database. Whether using pessimistic or optimistic locking, the goal is to balance data consistency with systems performance, ensuring that the libraries and patrons can interact with the system efficiently and reliably. By implementing appropriate locking strategies and addressing potential issues like deadlocks, the library system can provide a seamless experience for all users. So we have just discussed deadlock in quite detail, so I will actually skip. The problem with locking is that it can lead to a situation called deadlock. If the one program has resource locked and wants resource B, while the same time another program has resource B locked and wants resource A, you have a deadlock. Neither can proceed until the other releases the resource it wants, so they are both stuck in this situation. There are two main approaches of dealing with the deadlock. One is to try and prevent it from happening in the first place, and this can get pretty complicated. A second is just deal with it when it happens. Deadlock is not a very frequent occurrence, so if you can quickly resolve it, this is as good as preventing it in the first place. Versioning is an alternative to locking. You won't have deadlock, but you may require an application to redo its transaction. The assumption here is that simultaneous updates are not going to happen that often. Versioning could be consistent and considered to be optimistic concurrency control, whereas locking is pessimistic and concurrency control. Here we see the result of versioning. If John's transaction begins before Marshall's transaction, then Marshall needs to redo hers. Note that with versioning, you are not going to encounter deadlock. Data security is a critical part, as mentioned earlier, of any company's IT procedures, policies, and infrastructure. This is an important task for the DA or data architect and a DBA database administrator. Or data administrator, by the way, because data are critical resource. People in an organization must be sensitive to the security threats and take measures to protect their data. Data administrators are responsible for developing overall policies and procedures to protect databases. Database administrators administer database security on a daily basis. One is more managerial and the other is more technical. All of these losses can be very costly, or all of these losses can be very costly, and some can threaten the very existence of the company. Accidental losses attributed to human error, software failure, hardware failure, theft and fraud, loss of privacy and confidentiality, whereas loss of privacy is personal data, loss of confidentiality is corporate data, loss of data integrity, and loss of availability through sabotage. Threats to data security may be direct threats to the database. For example, those who gain unauthorized access to the database may then browse, change, or even steal the data to which they have gained access. But threats come from several places as well, so focusing on database security alone won't ensure the secure database. All parts of the system must be secure, including the database, the applications using the database, and the network, the operating system, and the buildings and the house, the database, and the all personnel who have access to the system. For static web pages, the security concerns are on access to the HTML files on the server. With dynamic web pages there is also concern about database access. Let's look into this with a library system example. Establishing internet security in a library system is crucial to protect sensitive data, ensures user privacy, and maintain the integrity of the system. In a library setting, this involves safeguarding patron information, book records, and transaction data from unauthorized access and cyber threats. One of the foundational aspects of internet security is authentication, which ensures that only authorized users can access the library system. This is typically achieved through the use of username and passwords, but more advanced methods like multi-factor authentication or MFA can provide an additional layer of security. For example, when a librarian logs into the system, they might need to enter a password and a code sent to their mobile device. This two-step verification process helps prevent unauthorized access, even if the password is compromised. Additionally, role-based access control, or RBAC, can be implemented to ensure that the users have access only to the data and functions necessary for their roles, further limiting potential security risks. Encryption is another critical component of Internet security, used to protect data both in transit and at rest. In a library system, encryption ensures that the sensitive information about such as patron records and borrowing history is unreadable to unauthorized properties and parties. When a patron access the library's online catalog to renew the books online, encryption scrambles the data being transmitted, preventing interception and misuse. Similarly, data stored in the library's database can be encrypted to protect it from being accessed by unauthorized individuals, even if they gain physical access to the storage devices. Firewalls and intrusion detection systems, or IDS, are essential for monitoring and controlling network traffic to and from the library system. Firewalls act as barriers, filtering incoming and outgoing traffic based on the predefined security rules. They can block unauthorized access attempts and prevent malicious software from entering the network. Intrusion detection systems, on the other hand, monitor network activity for suspicious behavior and potential security breaches. For example, if an unusual number of login attempts are detected from a single IP address, the IDS, or intrusion detection system, can alert administrators and take automated actions to mitigate the threat. Regular security audits and updates are vital for maintaining the effectiveness of the library's security measures. This involves periodically reviewing and testing the system's security protocols to identify and address vulnerabilities. Software updates and patches should be applied promptly to protect against known security threats. Additionally, staff training is crucial for ensuring that all users to the system are aware of security best practices, such as recognizing phishing attempts and handling sensitive data appropriately. By staying proactive and vigilant, the library can protect its digital assets and maintain the trust of its patrons. Three of the interesting web security projects called OWASP, or OWASP, Open Web Application Security Project, and at owasp.org. They have a great deal of the useful information for security and dynamic web applications. I suggest you look into that. Data privacy. Let's look into this with an example using the flower sales business. Data privacy is a critical concern in any given system. Let's use university management system as our example, where sensitive information about students, faculty, and administrative operations is stored and processed. Ensuring data privacy involves protecting personnel information from unauthorized access, misuse, and breaches, while also complying with legal and ethical standards. In a university management system, data privacy begins with the collection and the storage of personal data. Universities collect a wide range of information, including student names, addresses, academic records, financial information, and health data. To protect this information, the UMS, or University Management System, must implement robust security measures such as encryption, access controls, and secure data storage solutions. Encryption ensures the data is unreadable to unauthorized parties, both when it is stored and when it is transmitted across networks. Access controls limit who can view or modify data, ensuring that only authorized personnel can access sensitive information. For example, student academic records should only be accessible to faculty, advisors, and administrative staff who need this information to perform their duties. Transparency and consent are essential components of data privacy at university management system. Students and faculty should be informed about what data is being collected, how it will be used, and with whom it will be shared. This transparency allows individuals to make informed decisions about their data and ensures that the university is accountable for its data practices. Consent mechanisms should be in place, permitting individuals to opt in or out of certain data uses, such as sharing information with hired or third parties for research or marketing purposes. For instance, students should be able to consent to their data being used for academic studies or alumni communications, with clear options to withdraw consent at any time. Data minimization is another important principle in maintaining data privacy. This principle advocates for collecting and storing only the data that is necessary for the intended purposes. In a university management system, this means avoiding the collection of excessive or irrelevant data and regularly reviewing and purging data that is no longer needed. By minimizing data collection, universities can reduce the risk of data breaches and ensures that personal information is not retained longer than necessary. For example, once a student graduates, certain data such as course enrollment details may no longer be needed and can be securely deleted. To uphold data privacy, universities must also implement strong data governance practices and comply with relevant regulations. This includes establishing clear policies and procedures for data handling, conducting regular audits and risk assessments, and providing training for staff on data privacy best practices. Compliance with regulations such as Family Educational Rights and Privacy Act, or also known as FERPA, in the United States, and General Data Protection Regulations (GDPR) in Europe, is essential to ensure that data privacy standards are met. By prioritizing data privacy, universities can build trust with their students, faculty, and other stakeholders, fostering a secure and respectful educational environment. This work is protected by United States copyright laws, so make sure do not share this out of the university. So hopefully this has given you some decent understanding. Let's see you in the next lecture. Happy learning.